I will just pull up my notes, please hold on. Okay, so I guess all of you are able to see, right? Okay, so any doubts in how this inverter is getting implemented? Any doubts you can ask me. If not, then we can proceed. Working I had explained in the last class, but anyway, I will repeat it again. So whenever there is a zero here, okay, low value, T1 will turn on, VDD is connected, so the capacitor charges. So if it is charged, the output is 1. That is what I'm looking here. Now whenever I give 1, this transistor will turn off, okay, and T2 will start conducting. T2 is connected to ground, so since it's connected to ground, whatever charge is there in the capacitor, that gets discharged, right? So if it's getting discharged, it is bringing the value to 0. So this is the output function that you see. Okay, so this is how your realization of NOT gate happens. Okay. Next, all of you should make note of this rule here. Okay, please make note of these rules because this is fully dependent. Okay, these implementations are fully the circuit that you see towards the left hand side is fully dependent on these rules here. Okay, so just make a note of these. So the most important thing that we'll have to see here is for both NMOS and CMOS, NMOS and PMOS. Okay, whenever your NMOS is connected in series, okay, multiplication operation happens, it multiplies. Whenever NMOS is connected in parallel, then addition operation happens. So this rule you'll have to remember. Okay, whenever NMOS is connected in series, multiplication happens, and whenever they are connected in parallel, okay, addition operation happens. Now this is only for NMOS. Now let us check for PMOS. PMOS is just the reverse. When it is series for NMOS, it multiplies, but here there is an addition. Okay, and when PMOS is connected in parallel, they multiply. Now what are all these? Fine. Now let us take a circuit. Okay, now let us take a circuit. Now as you saw in the previous implementation, okay, whatever is the value given, we get the reverse value. So which means any CMOS circuit, if it has a PMOS and an NMOS, okay, an inverted value always comes out, okay, which means there is a bar, okay, the output is equal to the input bar, so it is negated. Keep this in mind, okay, this is a very important point, right? Now what I told you, when I put NMOS in series, they multiply. Now what is the, can someone tell me the equation of a NAND gate? How do we represent NAND gate? NAND gate, how is it represented? If inputs are A and B, okay, how do I represent a NAND gate? Or you can tell me what is the equation for NAND gate if the inputs are A and B? Okay, Rakesh says and plus not. Yes, good. So what is happening? We have an AND gate, okay, and it is negated, okay. So now let us first implement only the NMOS structure, okay. Let's implement only the NMOS structure. One thing that you should keep in mind here is that we are dividing the circuit, okay, into two halves, into two halves. Fine. So the first half is going to be your pull-up structure, okay, and the next half is going to be your pull-down structure. Now at the bottom we have NMOS transistors. All of you pay attention. At the bottom we have NMOS transistors, okay, and at the top we have PMOS transistors, right? This is our pull-up network and this is our pull-down network. So what is happening here? I want a multiplication operation and operation, right? So and is nothing but multiplication. And what am I implementing? NMOS. NMOS multiplication. So what should happen? It should be implemented in series. So what I am doing is I am connecting them in series. Okay, T3 is below T4. Okay, so T3 and T4 are in series. But if I connect them next to each other like this, okay, if I connect them next to each other, it becomes parallel. Okay, so this series part is done, right? Now what I have to do, the same thing I have to do reverse for my CMOS implementation. If they are series here, okay, then what should I do? In order to implement the multiplication operation, I have to put them in parallel, right? So T1 and T2, I am putting the same transistors, okay, in parallel. I am just naming them T1, T2, T3, T4 so that we get the count of transistors. Okay, we get the count of transistors and you will understand as to how this truth table works. Okay, now when you are writing in your examination, okay, writing this is not mandatory, okay, but you will have to write the first one, okay, inputs x1 x2 and the function f. Okay, these are important and this is not mandatory, okay. You may write it or you may not write it. If you write it, it's good, fine. Now so I have implemented the NMOS structure here, which is in series, okay, and the same thing I have done it in parallel. Now what is happening to the gates? Okay, the gates are getting connected to each other, okay, it is connected to each other. Now you can name them as A and B. I have just named them here as x1 and x2, okay, voltage x1, voltage x2, okay. And where will I get my output? My output will be exactly, okay, I have not drawn here. My output will be exactly where the two lines get connected, okay, this is going to be my output. So which means what I say is it is a junction, okay, a junction where your N transistor and P transistor gets connected, okay. So this, at this junction I'm going to get my output. Is that clear, students? Is that clear? So what are we doing here? We are first checking what is our equation. It is and means multiplying. So I'm going to check what is multiplying for NMOS. I'm going to connect them in series. Once it is done in series, always keep in mind the reverse is done to the pull-up network. If this is in series, I put them in parallel and I connect the gates. Okay, so this full thing is my CMOS structure. Upper section I connect to VDD just like our general structure, and the NMOS is connected to ground. Okay, so this is how our general structure is, and we use the general structure for the implementation of our CMOS circuits. So I hope this concept is clear. Are we clear till here, students? The NMOS and PMOS, how we are keeping them in series and parallel? Yes, Surya, thank you. Now, what we will do is now we will shift our focus to the truth table. Okay, since I have two inputs, so it is 00011011. This is our general combination of two-bit input, right? Now, I think all of you know how a NAND gate works, right? 00 should actually give me 0 in AND gate, but in NAND it becomes 1, right? And similarly, 1 should give me 1 in AND gate, but in NAND it is getting negated, so I get a 0, right? Okay, now let us take the first case. Okay, in the first case, when it is 0 0, so when I give 0 and 0, normally what should happen, since it's a low input, my T1 and T2 turns on, isn't it? Just like how we saw in our inverter, the same thing is happening here. Okay, and since it's a 0, my T3 and T4 goes off because they are in need of high potential, they are not in need of low potential, right? So T3 and T4 are off, T1 and T2 is on. So what happens if T1 is on? Okay, VDD gets accumulated or it gets passed to the output. And what is my output here? 1. So am I getting 1 VDD? Yes. This is how you have to analyze. Okay, fine. Now let's take the next case. Okay, now in the next case, or we will take 1 1. Yeah, 1 1 will be better. So in this 1 1 case, T1 and T2 is off, which means there is no VDD going to my output, which means the capacitor is not getting charged. So T3 and T4 is on. So whatever charge was there in the capacitor, that is dragged down to what value? Ground value, which is 0 value. So T3 and T4 is on, T1 and T2 is off. So what value am I getting? I am getting 0. So isn't it the same thing which we spoke about, drawing the value down to ground, right? So this is how you have to analyze your truth table, and this is how you will know if your circuit is correct or not. So students, have you understood how we implement the CMOS circuits? Yes, thank you. Now
Sir,
keep
can you
in
repeat
mind,
the truth table again?
you want me to repeat the truth table? Okay. So this time what we will do is we will take which case you want me to take? This was,
Yes, sir.
sorry,
Second case, zero
second
one.
case will take. Okay, fine. Okay. So as your friend said, we will take the second case, which is 0 1. Okay, and here since it is 0, what is 0? X1 is 0. So where is X1? X1 is here. So I'm putting a 0 here, and X2 is 1. X2 is 1. Okay, so where all is it connected? Wherever it is 1 here, so T4 will turn on, isn't it? Because it's a high value. So 1 is passing the gate to the gate, so T4 is on. Now here T2 should turn off. Why? Because it is a high value, right? So this is done, and this is done. Okay, T2 is done. Okay, T2 is done. And now let us see T3. T3 is having 0, so which means it is a lower value and it's a NMOS. So normally NMOS needs what? High value, right? So which means it is off. And T1 is getting 0. So this 0 passes here, right? 0 is passing here and T1 is getting 0 value. So which means T1 is turning on. So I think this part you have understood, isn't it? This was, this section is understood, right? If PMOS is getting a 0, it will turn on, and if NMOS is getting 1, it will turn on. So this case you should remember. Okay. Now what is happening to my output? Now since my one of the transistor is on, okay, and the other transistor is off. Okay, so which transistor is on here? T1 is on. Okay, let me use another color so that will be easy. Okay, so T1 is on. Okay, and which is the other one on? T4. T4 is on. Okay, now since T3 is off, okay, since T3 is off, the circuit is not complete. It cannot discharge the capacitor. Okay, but you can see that there is a path from this transistor to the output. So which means I should get from VDD to the output, the capacitor is getting charged. So I am getting an output 1. Is that clear? This was, since it is parallel.
Yes.
Yes, since it is
Yes.
parallel. Even if this transistor is off, see, T2 is not working, but I have an alternative path here. Okay, instead of this path, the VDD can take the path through transistor T1. See, ultimately you should understand transistor is also a switch. Okay, so this switch is turned on. So since this switch is turned on, VDD will actually pass through T1 and it reaches output. So since there is a connection between my VDD and my capacitor, what will happen to my capacitor? It should charge. Now, is there an option for it to discharge? No option because T3 is off. So this is a series line. It is just like a chain, right? If one of the link is broken, do you think the chain will hold on? This was, I want you to respond.
Sir?
If the chain, okay, this T3 and T4 is like a chain, okay. So if one of the links in a chain is broken, do you think the chain will still hold on?
No, sir.
Not at all, right? So the same thing is happening here. So your T3 is broken, okay, and T4 is working. So there is no connectivity between my capacitor to my ground. So there is no way that it can discharge. It can only charge through this path. Okay. So this is how you have to analyze and understand your circuit and your truth table. Okay. Is that clear, students? Can I move on to the next one? Okay. Now, let us see the next case, NOR gate. Okay, forget about the truth table. Okay, this truth table is very simple because you already know 00011011 and you know what functions you have to get, what output you have to get, and you know that if there is a 1 for the NMOS, it will turn on. If it is a 0 for a PMOS, it will turn on. So, which means we are done with this truth table. Right. Now let us concentrate on the implementation of the circuit. Okay. Fine. Now what's the question asked? The question is telling us to actually implement a NOR circuit. Right. So I should understand I am going to take OR. Okay. OR means what? Adding. And the negation will automatically happen. So if you can recall, if I have to add two components using NMOS, I should put them in parallel. Okay, whatever you do at the bottom is done reverse for the upper section. So I keep two transistors here, which is in parallel, and then I keep them in series at the above section. Now remember I told you we divide the circuit into two halves. right? So this is the lower section, this is the upper section. Upper section is your pull up network, right? Your pull up network, and the down one is nothing but your pull down network, pull down network, right? Okay. So get back to this rule here, okay, to this rule, and this rule you should always remember. So sometimes I understand that it gets confused for you to remember series, multiply, parallel, add. So remember only for NMOS. Okay, the reverse you can do for PMOS. So if it's in series, you're going to multiply. If it's in parallel, you're going to add. Just remember only for NMOS, because whatever you do for NMOS, it's reversed in PMOS. Series, multiply, series, add, parallel, add, parallel, multiply. So either you remember PMOS or you remember NMOS. I suggest you remember NMOS. Okay, so before you start implementing the circuit, you write this rule, okay, and you can use this rule for any implementation. Now since we have a or here, which means it is adding, and I'm implementing an NMOS, add NMOS, so parallel, right? So I keep both of the transistors in parallel. Now what do I do to my PMOS? Just the reverse. I keep them in series. So just put two transistors in series and connect the gates. That's it, right? So this transistor connects here and this transistor connects here. Okay, so this is how you implement your NOR gate. Now let us see one of the case. Okay, one of the case as to how this truth table or how this circuit works. Okay, now we will take probably, let us take a worst case, on, off, off, on. Okay, let us take this case. Okay, fine. Now here uh, x1 x1 is 1, x2 x2 is 0, right? 1 and 0. Okay, now wherever the 1 is going, okay, t1 should be off, done. Next 1 is going here, t3 should be on, done. 0 is here, okay, so since 0 is going here, my t4 should turn off, t4 is off, done. 0 is getting into t2, so it should be on, done. So 1 plus 0 is actually 1, but since it's a NOR gate, I am getting what? I am getting 0, right? This is also done. Fine. Now for this combination, we should actually get the output 0. How is it happening? Now 1 is passed here, okay, and you have VDD here, and then you have your, uh, say you have your capacitor connected, okay, you have your capacitor connected across your output. Now since there is a 1 here, okay, and t2 is uh, since it's a 1 here, this is actually broken, which means this switch is off and this is on, so I cannot pass VDD to my capacitor. Will it happen? Someone respond, will it happen? Because t1 is broken, right? So which means I will not get VDD. Okay, now let us take the other case. In the other case, T3, T4, T3 is on, okay, T3 is on and T4 is off. Okay, so let us put T3, just a minute. Okay, So we were seeing this case, right? Okay, so T3 is on and T4 is off. Okay, so I will need to mark this, and T1 is off, so this transistor doesn't work. So I have only T2 and T3 working. Now since T2 is working and T1 is broken, do you think there is a connection between VDD and output? Students respond. Is there a connection? No. Good. Now let us come to the lower case, okay, which means the pull down network. Now since this is in parallel, okay, and okay, let us put in the values. Put in the values x1 s1 and x2 0. Okay, now I have the values here. Okay, and okay, so I have my 1 here, which means T3 is conducting. Okay, since T3 is conducting, and as I told you, I have a capacitor which is connected across my output. Okay, now this, since T3 is here, it can actually discharge the capacitor to ground. Since it is discharging to ground, I should get 0 value. So are we getting that 0 value here? Right? So this is how you have to analyze. Now analyzing is the next part. The first thing that you guys should understand is how to implement. Okay, so implementation part you should understand. At this level, okay, you will not be asked to analyze a circuit. Okay, keep in mind, you will not be asked to analyze a circuit. You will just be asked realize a NOR gate using CMOS technology. That's it. Okay, now similarly what I want you to do is look into the last example here that we have, which is nothing but implement y is equal to a into b plus c. Now this is a complex, a little complex problem that we have here, where I have a combination of addition as well as I have a combination of multiplication. So what I do is I break them into parts. So first I will try and implement the b plus c. Okay, so I will break this into two halves. Okay, first I will try and implement b plus c. Next I will do the multiplication. So that is my plan. So for addition, what I have to do, I have to take them in parallel, right? So b and c are in parallel for NMOS, so which means this is done. B plus c is done. Next, what is happening? A is getting multiplied with b plus c. Multiplied means what? I have to put them in series. So A is in series with B and C. So wherever my NMOS and PMOS gets connected, okay, at that junction I'm going to take my output. Right? See this section. So at this section I'm going to take my output. So my pull up transistor is here and my pull down transistor is here. Now observe this very carefully. B and C is parallel. Here it comes in series. Okay, A is in series with combination of B plus C. Here A is parallel to B plus C. Are you getting it? Yes, students, whatever we do for NMOS, the same thing we reverse it for PMOS. Are you all getting it?
So once more, sir.
Once more? Okay, fine. Now we have an equation. What's the equation? Y is equal to A into B plus C. Okay, this is our equation. So in this case, I have both addition as well as multiplication. So first I will implement this. It's up to you, however you implement, but I will tell you this is the easiest way to do. First I will implement B plus C, okay, because I have majority terms here, two terms here, and then I have just one term which is A getting multiplied to this combination, right? So I take B plus C, okay, so B plus C here is adding, so I keep them in parallel. Okay, B and C is in parallel. Now always you have to look at those rules keep in mind. Okay, looking at the rules is very important. Fine, the one which I had written on the right hand side. Okay, fine. And what we do here is next a to be multiplied with b plus c. Right. So when a is getting multiplied, what I should do? I should use the series combination. Series means what? One after the other. So I should place my a on top of the parallel combination of b plus c. So what I should do? I should connect it with a line. Okay, I should connect it and then I bring my transistor. So this becomes my series combination. So a is in series with parallel of b and c. Now the reverse thing happens here in my pull-up network. Okay, so what is that reverse thing? B plus C, it's in parallel, but here you observe, is it in parallel, B and C? It is one below the other. Whenever it is one below the other, it is series. Okay, B and C is one below the other, so which means it's in series, right? Now A is in series with this combination, but I have to bring them in parallel. Parallel means what? Next to each other. So I have brought A in parallel with B plus C. Is this clear, students? Okay, anyway, I will be posting this video. Okay, you can go through it, and still you have doubts, we can continue in the next class, no problem. Okay, so um, uh, is that clear, Rohit? Have you understood the concept that I have taught? Yes.
Yes, sir. Yes, sir.
Okay, fine. Now an alternative approach. Okay, I have A into B plus C. So what I can do is I can even make it as AB plus AC, or let us take another example. Okay, let us take this example AB plus CD. Okay, now you guys try to analyze how this is done. AB is multiplied, CD is also multiplied. So whenever there is a multiplication, I put them in series, right? CD multiplied, AB multiplied. Now now uh, now you can see that AB is added with CD. So AB comes in parallel with CD, right? Now AB is in series here, I put them in parallel. CD is in series here, I put them in parallel here. Wherever my NMOS structure and PMOS structure connects, there I take my output. Okay, so I think we will stop here. Okay, and we will continue in the next class with regards to uh, the upcoming topic, which is nothing but your uh, just a revision of logic gates and how they are represented. Okay, so we will see in the next class. Okay, fine. So I'll be posting in the attendance in some time. Thank you.